We'd like to start with a big welcome for Helen Kwan. Come on up here, Helen, and take my job.
Thank you.
Thank you. Please, guys, let's give her a little
you.
love. There we go. Hong Kong PolyU alumni Helen Kwan, ladies and gentlemen. Helen, the stage is yours.
Thank you, Andrew. Thank you for the really warm introduction, and good afternoon, ladies and gentlemen. Welcome all to the PolyU Spotlight, Building a Reliable and Secure Web3 Ecosystem, proudly presented by the Hong Kong Polytechnic University here at WOW Summit Hong Kong 2025. This special session is organized by the Research Center for Blockchain Technology, RCBT, at PolyU. RCBT is a leading research hub dedicated to advancing blockchain technologies, advancing security, and fostering innovation for the Web3 era. The center actively brings together scholars, industry experts, and innovators to drive impactful research and real-world applications. Today, we are proud to showcase some of the latest research from the PolyU's emerging leaders. You will hear from 4 speakers who will explore topics ranging from large language models in Web3, Web3 security, cryptography in Web3, and the challenges facing Ethereum. At the end of the session, we've also prepared some PolyU design souvenirs, so stay tuned with us. And without further ado, let's begin our session with a warm welcome. Please join me in welcoming our host, Professor Daniel Xiaopu Luo, Associate Dean Research of the Faculty of Computer and Mathematical Sciences, Professor of Department of Computing, and the Co-Director of the Research Center for Blockchain Technology of the Hong Kong Polytechnic University. Let's welcome Professor Luo, please.
Thank you. So, good afternoon, everyone. On behalf of the Hong Kong Polytechnic University and the Research Center for Blockchain Technology, I would like to extend a very warm welcome to everyone to be here at our special session, PolyU's Spotlight, Building a Reliable and Secure Web3 Ecosystem. So, as Web3 continue to evolve, we witness not only innovations, but also new risks from smart contract exploits to security gaps and vulnerabilities. It's clear that much work remains to shape a safer and more resilient Web3 ecosystem. So that is why we believe research-driven development is more important than ever. So today, I'm especially proud to introduce a group of rising stars from PolyU. New bright minds bring new energy to the Web3 research community, including Professor Amelia Lee, Professor Kai Zhou, Dr. Xinye Lu, and Dr. Ning Yuhe. So they will introduce their latest research on this very exciting area. So without further ado, the stage is theirs. Thank you.
Thank you, Professor Luo. Please take a seat. Now, our first speaker of today is Professor Jing Amelia Lee. Professor Lee is an associate professor in the Department of Computing at the Hong Kong Polytechnic University, and she will speak on the topic, how LLM writes code, and what does that mean for Web3. Professor Lee, please.
Thank you so much for coming here, and I really appreciate the invitation from Professor Luo. Actually, I'm not a Web3 researcher. My research focuses on large language models and natural language processing. So today, my talk will center on what is large language models and how large language models can be further applied to Web3 through their capabilities to write codes. Okay, so my title for today is How Large Language Models Write Codes and What That Means for Web3. Okay, so let us look at the trending topics in today's world. As can be seen here, we're discussing a lot of things all about large language models. We're talking about ChatGPT. We are talking about DeepSeek. We are talking about a lot of large language models. So it seems that the trending topics in the world today are about large language models. And I'm very proud of it because it's origins from the area named as natural language processing, or NLP. And this is actually a sub-area in artificial intelligence. And so I understand that today many researchers are actually not specifically focusing on the research in AI. So I'm going to briefly talk about what is natural language processing. And you know that artificial intelligence goal is to enable machines to gain a lot of human intelligence. And one of the most important intelligence humans are very proud of is the capabilities to use language. So the mission for NLP researchers is to develop AI models which will be able to use natural language well. So you know that it's actually a fundamental capabilities for AIs to pass Turing test, right? To behave just like humans so that they can communicate with humans in their languages, right? So basically here, NLP involves two important tasks. One is natural language understanding, which focuses on how to enable machines to read. And the other capabilities is natural language generation, which focuses on how to write in human languages. You know that today, NLP models such as ChatGPT and a lot of large language models, they are very good at not only understanding generation, but seems to gain the capabilities to have high-level human intelligence, such as reasoning, planning, and decision-making, right? This is actually I'm actually very proud of it because you know that, when you are so good at language skills, it exhibits the capabilities to gain high-level thoughts like reasoning, planning, and decision-making. So it means that maybe language is the jazz of thoughts, right? You know that if you are so good at language and you read a lot of things, then you can gain the capabilities to think, to reason, to plan, to make decisions. And if we will be able to ground these capabilities into like real-world environments, for example, we can actually ground this super smart brain on the web, or we can ground it in our physical world so that they can interact with the environments and behave just like humans. So, I'm very proud of that because large language model seems to be a very, very clever brain, and we can actually ground it in a lot of real-world scenarios so that they can help us just like human assistants. Okay, so in order to know how large language models will be helpful in the area of Web3, I'm going to talk about three parts. The first one is how advances in NLP led to large language models. So I'm going to talk about the history of natural language processing and to help people here understand why we have LLMs today. And then I'm going to talk about, how LLM write codes. So that we can gain a better understanding of how NLMs can be applied to Web3. And then I'm going to talk about my thoughts, what that means for Web3 from, it's actually, as I said earlier, I'm not like a Web3 researcher, so I'm going to talk about that from an NLP researcher's perspective. Okay, so let's first get started with the first part. How advances in NLP led to large language models? So basically, I started my PhD before 2013, and at that time, NLP was considered as a collection of various language tasks. For example, we may have researchers specifically working on sentiment analysis, which focuses on how to enable machines to understand humans' emotions and sentiment. And we also have like researchers specifically working on like Chinese word segmentation or like NER, named entity recognition, and so forth. So at that time, NLP was considered as a collection of various tasks, and researchers are working on their within their groups to advance their specific task. And at that time, you see that on the right, we show a very typical architecture of NLP models at that time, where we will have like a neural network like this, and then we will feed in the data like through the input layer, and there should be like hidden layers learning the parameters and the output layers for providing the outputs. Right? And at that time, it was very popular for model training in an end-to-end manner so that we don't need to actually care about what parameters are learned, right? We just feed in the data and let the models figure out the parameters on their own, right? That enables easy training, but the challenge is that we have no ideas about the features, and the features are specifically related to the task. So we can only learn task-related features. And obviously you may see obvious weakness here because a lot of tasks have shared features, right? So then in the next stage, people start to think about how to learn these fundamental features which can be shared across tasks, right? So we may need these specific we may need these fundamental features or universal features to enable models to advance the performance of a lot of tasks instead of only advancing task-specific performance. So the second stage in NLP, we name it as the word embedding area. What is word embedding? They are like word vectors which can exhibit word-level semantics, which can indicate meanings, and they can be seen as the word-level features at that time. So on word level, we will be able to indicate fundamental representations or features which can be applied to a lot of tasks, right? But you can see that the weakness of this type of the models is also, is also very obvious because the features or the embeddings are only learned on the word level, right? And so the next stage is to think about how can we learn sentence level features which can be applied to a lot of tasks so that the model will be able to exploit a longer or richer context. So we have the stage 3 model represented by BERT, right, which was proposed by Google, and that's very powerful because it starts an area of pre-training and fine-tuning, right? Recall that earlier, the NLP paradigm is like end-to-end training, right? We don't care about the parameters, just feed in the data and let the model figure out what the parameters should be. But here, we will first do a pre-training where the models will be used to do a lot of reading so that they understand better about the data and they will be able to gain fundamental natural language understanding capabilities, right? And then we can further narrow down these capabilities into task-specific skills like sentiment analysis, question answering, machine learning, and so forth. So in this way, we don't need to have a lot of task-specific data, right? We don't need to have like a lot of sentiment analysis data. We don't need to have a lot of machine learning data, machine translation data. What we need to do is to have a lot of unsupervised data, right, unlabeled data for the model to explore and learn the fundamental language skills, and then we can narrow down the skills to task-specific scenarios. So that is the third stage. And you may see that in this stage, the models may be very good at language understanding. And then in stage 4, we see that the model will be able to gain superior performance in not only understanding, but also generation, right? So this is the ChatGPT area you see. And a lot of people may think, okay, so can we just forget about the embeddings, or like can we just forget about the the sentence level features or the word level features we previously developed? So basically here, we cannot forget, we cannot just ignore the previous history, because these capabilities will help us, fit in the specific data that we need for domain-specific tasks. So we know that these ChatGPT-like models, they are like general models, right? They have like good general capabilities, but these capabilities may not be able to be narrowed down for domain-specific areas because they don't have the data. And we need to feed these data into the models through retrieval augmented generation. So we need to have the embeddings. We need to have the the sentence level features or word level features to help us identify semantically similar data so that we can fit into the model to learn the domain-specific capabilities. So that should be the stage 4, where we have like a powerful generation model, and it should be equipped with like a small embedding model so that it will be able to find the data that the model needs. Okay, so here I'm going to briefly talk about our previous work named as Angle, which has million-scale downloads on Hugging Face, and it's still available there. And it's very helpful for us to, for given a query, and then we will be able to find semantically similar data so that we can actually find the domain-specific data to feed into the large language model so that they will be able to understand the domain-specific queries and provide sufficient to provide answers in an appropriate way. Okay. And then I'm going to move on to talk about more advanced skills for large language models to write codes. We know that large language models are very good at language skills, right? And you know that programming language are somehow look like natural language, right? Because they are like strings. So how can we expand these capabilities of language understanding and generation for code understanding and generation? So that's actually a very obvious expansion because as we said earlier, that natural language has like high similarity with programming language. And here I'm going to talk about two specific tasks. One is about source code understanding and generation, and the other is binary codes. So I'm going to talk about the first work related to code search. Recall that earlier we said that embeddings models will be able to help us find semantically related text, and it can be actually extended to code search. And you see that the results are quite amazing. And we also shared the model on Hugging Face so that everyone can benefit this advance. And then we also further advanced that for prompt engineering, and we develop better retrieval models for code completion, and the model performance on a lot of tasks are advanced. Then we also expand that for binary codes. We see that decompilation is very similar to translation, to machine translation. It's just like translating one language to other. And while for decompiling, it's like translating from binary codes to source codes. So we also pre-train a decompilation model with large language models so that these models can do decompilation. And this model is also shared on GitHub, and it has thousands of stars. So if you're interested, you can also download it on the GitHub website. Okay, so at last, because of time limitation, I will need to quickly wrap up for what we discussed earlier and also share my thoughts about what that means for Web3. So the core challenges here, large language models just like are not only be providing tools, they can also gain human-like intelligence. So we are like wondering if they will be able to provide better assistance for Web3 applications. Okay, so that they can be providing infrastructure for security, interoperability, and automation. So I'm going to talk about that in three perspectives. One is about code generation for smart contracts, because earlier we said that our large language models are good at code generation, right? So we are interested in if it can be used for smart contracts, and interestingly, I'm going to share a little bit about my thoughts, and I found that maybe it's possible because different contracts on different chains may use different languages, and we will be able to actually do translation with large language models benefit from its superior language or code capabilities. However, there should be several thoughts that I'm going to share with you. One is the severe hallucination problems with large language models. We need to have like very accurate results. We don't need these accurate hallucination results. So how to deal with that's a challenge. And the other is how to deal with the training data sparsity, because we know that training data is like a very important features for large language models. So, we may have like sufficient data for one language, but if we do that for the other language, we also need to have a lot of data. So how to deal with this data scarcity with like, automatic data generation or collection would be like a very sexy problem to solve. And the next one is to use the compilation model for security analysis, because the compilation will be helpful for us to actually translate binary codes back to source code. So it provides better, interpretations for security analysis. The auditors can use it to understand better about the binary codes. However, the problem is that, the compilation languages like the codes or the binary codes, they have like specific structure, and we needed to help the models understand this structure to provide more advanced help. And the other challenge is that because that these tools can provide new potential for attackers, right? So how to deal with this adversarial attacking with decompiling focused large language models can be another interesting topic to explore. And the last one is code search for auditing and exploit analysis. For auditors and exploit analysis, sometimes they want to search related codes, and with large language models, they can have like better results with better semantic understanding capability. However, we know that the semantic on code is different from the semantic on languages. So how to understand the semantics on like this specific codes, or like how to evaluate similarity would be another interesting topic to explore. So to summarize here, I talk about the potential for LLMs to be to provide not only a tools but also be engaged in the infrastructure of Web3 security, transparency, and governance. And it's like a double-edged sword because large language model is not perfect, so we want to make it better and better to fit better into these applications. And the last message is that we need collaborations. NLP researchers and Web3 researchers should work together to advance a better world with Web3. Thank you very much.
Thank you, Professor Lee, for the fascinating insights into how large language models intersect with Web3. Please take a seat. Now, our next speaker today is Professor Kai Zhou. Professor Zhou is an assistant professor in the Department of Computing at the Hong Kong Polytechnic University, and he will be presenting on the topic securing Web3's ecosystems through robust graph-based anomaly detection. Well, let's welcome Professor Zhou.
Okay, good afternoon. So I'm very happy to be here to share some of our latest research. So my main research focus is on AI security, specifically adversary machine learning. So recently, one line of our research focused on graph-based alarm detection. So in today's talk, I'm going to introduce how we're going to make these tools more secure, and at the same time, how we can utilize these more secure tools to secure the Web3 ecosystem. Okay? So graph-based alarm detection belongs to the broader area of graph learning. So that's a branch of machine learning that focuses on the analysis and interpretation of data represented in graph forms. So it becomes very popular because we find that many real-world systems can be actually represented as graphs. Right? For example, we can represent entities using nodes and use some attributes to describe their entity, and use edges to represent relations among entities. Right? So throughout the history, we have many graph learning models, such as shallow models like random works, matrix factorization. And about 10 years ago, when with the rise of deep learning, we have graph neural networks. Right? That's how we apply deep learning models over graph data. And more recently, we have graph foundation models. That's where we train the model over massive data and possibly integrate language models to solve various graph tasks. So using these different models, we can actually solve load classification, for example, how to classify the node in a graph, or link prediction, right? How to predict whether there exist some links among the nodes, okay? So graph-based alarm detection is actually a kind of a task, right? We can use all these kind of graph models to find out the anomalies within the graph data, okay? So why do I care about graph for Web3? The apparent reason is that the transaction networks is naturally represented as a kind of graph, right? We have all kinds of accounts that can be represented in nodes, and the transactions can be represented as edges, okay? And moreover, something that does not appear to be a graph at a first glance can be actually represented as graph, okay? So one example is the smart contract, okay? So smart contract is a piece of code, right? And we can actually use some analytical tools to represent a smart contract as a kind of graph. Okay? So this gives you a sense why we can use the graph models to address security challenges in Web3. Okay? So as the defender, we can actually develop a lot of alarm detection tools, right, to try to find out anomalies from graph data. And importantly, these anomalies actually corresponds to bad behaviors in our real lives, right? They may correspond to suspicious accounts. They may correspond to malicious smart contract, okay? So that's the first side of the story, right? As a defender, we want to use tools to find out anomalies. But on the other side, the attackers are also intelligent, right? They are not fools. So given that they can see what kind of tools is actually deployed in reality, they can find out ways to evade the detection, right? That's so a story of two sides, right? Attack and the defense. So that's why the security of the tool itself is crucial. Okay, we want a more robust tool to find out anomalies. So this picture summarized the two broad missions of our research. Okay, so first we have the first mission: how can we make the tool itself more robust? Okay, so we take a three-step strategy to achieve this broad mission. So first, we're going to study how we can actually attack these kind of tools to find out their vulnerabilities. And then we want to develop some effective techniques, right, to improve the security of these tools, okay? But we're not satisfied. So in the third step, we're going to study the theoretic properties of these techniques. We're going to provide a kind of guarantees about the tools, okay? So now we have developed much better tools. The second mission is actually how we are going to use these better tools to tackle the challenges in Web3. Okay, so in today's talk, I will briefly mention two cases of our recent work. So one is how we can use graph-based alarm detection to find out criminal groups in transaction networks. The second is how we're going to use detection tools to find out adversary smart contract. Okay, so before that, let's focus on the mission one. So the first step is how we're going to attack an existing graph-based alarm detection tools. Okay, so basically we're focusing on a kind of attack that the attacker can somehow manipulate the data, the input data to the graph learning models. Right, we have a graph learning model F. It has a kind of graph G as input, right? It will produce some predictions FG. So the attacker can somehow modify the input graph G to manipulate the predictions of the model. Okay, this is a typical kind of adversarial attack. Okay, so we can actually divide this kind of attacks into two broad categories. The first is that the attacker can modify the test samples, the test input, while the model itself remain fixed, right? This is called evasion attack. The other is that the attacker can somehow poison or pollute the training data set of the model, right, so as to crash the model, right? That's called a poisoning attack, okay? So why do we care about this kind of data manipulation attack? Because the action, the meaning of data manipulation actually corresponds to many real-world malicious behaviors, right? For example, when you change your account profile, you are actually changing the attributes of the nodes in the graph. When you are changing your transaction behaviors, you are actually changing the topology of the graph, right? So we spent a lot of efforts on the first part, right? How to attack graph learning. So we have several publications in this direction. We have attacked alarm detection, and we have attacked social network analysis tools, trust prediction in cyberspace, and malware detection, and recommendation systems. Okay? So we proposed many practical methods to show the effectiveness of these attacks. And the take-home message is that even though these intelligent tools are very effective, but in fact, they are very vulnerable to this kind of data manipulation attacks. Okay? So the second step, given these kind of attacks, how can we actually improve the robustness of the models? Okay? So our goal is that we want to retrain or get a better model F prime, right? Even the data itself is manipulated. We want to make sure that the prediction will stay the same as before, right? So we also have several works on this direction, and we proposed a series of techniques to make the model more robust faced on attacks. Okay? So we primarily focus on some fundamental models like GNN or graph contrast learning. And one of our recent works also proposed a very efficient retraining methods, because you know there's actually a gap between a normal model and a robust model in terms of training complexity. So our recent work actually mitigates this kind of efficiency gap. Okay? So it seems that we are quite good, right? We have a more robust tools, but in reality, we have a more concerning problem. Okay? So remember this figure from the previous slides, right? Even though we are now equipped with more robust tools, but remember that the attackers are intelligent, right? They can invent, they can compose more powerful or new adaptive attacks, trying to evade the existing robust alarm detection tools. Right? It's like an arms race between the attacker and defender. Okay? So underlying reason is that we lack some theoretical guarantees on these detection tools. Okay? So these tools might perform well in some cases, but they are not guaranteed to be robust against future or unseen attacks. Okay? So there's an emerging research direction. So we ask this kind of question. So can we guarantee that the detection tool is always robust, even against a kind of attack that is not seen at the moment? Okay? So the techniques we are using here is called certified robustness. Okay? So it means that we can somehow mathematically prove that the tool is robust against any kinds of attacks, even though these attacks is not seen at this moment. Of course, we have put some constraint on attacks, such as the power of the attacks, right? This is actually a very reasonable constraint, okay? So following this line of research, we also have some works. We are inventing some techniques to make the graph neural networks certified robust against attacks. We can actually provide a formal mathematical certification on your graph models. Okay? So for example, we have invented a bi-smoothing technique for protecting GNNs, and a more efficient version called a collective certification. And we also studied a specific attack against the backdoor attack. So through the mission one, we actually have a very robust tour, even with theoretic guarantees. So now the second mission, how can we apply these tours to solve security problems? So I will talk about two cases. One is about group-level alarm detection in transaction networks. So we know that we can form a transaction as a kind of graph and try to identify some anomaly nodes from the graph. But actually, we find out that the criminals in reality tend to form a kind of group, right? So figure 1 shows a real case of 4 companies involved in money laundering, okay? So they actually form a kind of path structure, okay? So these criminal groups tends to have a specific topology patterns. So this is an issue that cannot be can be resolved by previous research works. So for example, in figure 3, we have actually 3 groups, right, in different colors. When you apply some kind of the state-of-art works to detect anomalies, you will find that they cannot identify the anomalies inside the group. The reason is that these kind of methods primarily utilize the nature that the anomaly nodes are quite different from their labels, right? But when you consider a node inside the group, these kind of methods will fail. So these motivates us to consider detection anomalies at the group level instead of individual levels. So we actually proposed a very nice graph learning models based on graph contrast learning. This allows us to tackle this challenging to find out anomalies in group levels. So I will omit the technical details. So the second case is actually about finding out adversary exploiter smart contracts. Okay? So we focus on special kind of malicious contracts. They are called adversary exploiter contracts. Okay? It's a kind of malicious contracts that is designed by attackers to exploit vulnerabilities in other normal smart contracts. Okay? So these kind of contracts does not contain vulnerabilities itself. So instead, an attacker will deploy these kind of contracts, and they will actively explore the vulnerabilities of other contracts. And in the end, the attacker can get profits from transaction activities. Okay? So in our recent work, we first find out a way to build up a kind of a graph to represent smart contracts. Okay? So this is called the semantic relation graph. So we mainly enforce some semantic meanings over the graph representations. Okay? And then given this graph representation of smart contracts, we proposed a new detection model. So besides a normal graph model F, we actually incorporate a module that is used to explain the prediction results. Okay? Because you know for normal machine learning models, they will give a prediction results, right? So explainability means that other than the prediction results, I'm going to give out a piece of data which explains why the model make that decisions, right? So our new approach can make predictions and also give explanations, which is a subgraph, explain why the current smart contract is anonymous. Okay? And moreover, this explanation model is self-explanatory, meaning that this model will enhance the prediction task itself instead of post-explainability. Okay? And this self-examinability actually brings a lot of advantages. For example, it is more data efficient. We can actually use less labeled data and achieve better detection results. And also it is more robust against several adversary evasion attacks. Okay. So finally, some take-home message. So nowadays we are talking about AI security, and it actually has two aspects. So one is security of AI, right? It's about how secure the tool itself is. The other aspect is security is about AI for security, right? That's how we use AI to solve security problems. So through our experience, we find out that an AI-based secure tool itself can be the attack vector. Okay? We have many effective attacks. But fortunately, we have a lot of techniques to make the tools more robust. But be cautious of adaptive and unseen attacks. Right? The attackers are always intelligent. They try to evade the existing tools. And now we have a very promising solutions. Okay, we can somehow provide theoretic guarantees on the detection tools to make it probable, to make the defense provable secure. Okay, but actually for this kind of secure theoretical tools, efficiency is the major issue. Okay. So many researchers are actually working on this direction to bring these theoretical tools to practice. Okay? And finally, our mission is to develop more effective, robust, and explainable tools to address security challenges in Web3. Okay? So that's all about the sharing. Thank you.
Thank you, Professor Zhou, for showing us how graph-based methods can strengthen Web3 security. And next, we have Dr. Xingye Lu, a research assistant professor in the Department of Computing at the Hong Kong Polytechnic University. Dr. Lu will present the topic, the role of cryptography in blockchain. Please welcome Dr. Lu on stage.
Thank you for the introduction. So today I'm going to talk about the topic that lies in the heart of the blockchain, which is the cryptography. So we know that blockchain provides a property of decentralization, security, and also transparency. This is not only depends on the consensus protocol or the network, but also provides by the underlying cryptography algorithms like hash functions or digital signature schemes. So today I'm going to talk about some advanced signature schemes and its applications in blockchain, and also a quite attractive topic in recent years, which is zero-knowledge proof, along with some kind of our works on this field. So digital signature schemes provides people the power that to demonstrate to other people some kind of data, a piece of data or a file is actually it's actually sent from itself. So basically what people do is using the secret key to sign a file or data and let other people to use the public key to verify it. So the authenticity that only the people with the secret key can generate a valid signature, and the integrity that once the file or the data got a little tampered, then the signature will no longer valid. So these two kind of properties allows us to apply digital signatures in the blockchain systems to allow people to approve transactions. So in the blockchain systems, a user uses the secret key to generate a signature on a transaction to approve these transactions, and then the network will use the corresponding public key to verify whether the transaction is a valid one or not. But in some kind of cases, instead of using one single key to approve a transaction, we may want some kind of other properties that we may want to distribute the signing power among multiple parties, or like to distribute the account management, this kind of power among multiple devices. So this is where multi-signature schemes come to be useful. So in the multi-signature schemes, you require some threshold members to agree to a message. For example, like you distribute the power of signing to n users, and only if T of the users agree with the message, you can generate a signature on it. So this kind of setting provides some kind of protection against key loss, because even one of the keys gets stolen, the adversary still cannot touch the assets inside this account. And also, it can let a lot of devices or organizations together to collaboratively manage an account. So to achieve multi-signatures, there are several ways. The most trivial one is like in the Bitcoin. For example, like the Bitcoin allows 2 out of 3 multi-sig address. So what it means that, so there are 3 public keys here. If you provide enough signatures, so here, if you provide 2 signatures for it, then you can unlock this UTXO sent to this multi-sig. So here, this naive multi-signature schemes has one drawback. It is that you need to append enough signatures on it. For example, like it is 2 out of 3 multi-sig, then you need to append 2 independent signatures to it. So it will increase the transaction size. So one challenging problem here becomes that how could we achieve the multi-signature, this kind of property, without increase the signature size? So here the aggregate signature schemes, which is not used in the account management, but can help us doing the multi-signature task. So what it do is that for each of the user, it will have a pair of public keys and secret keys, and each of them can generate a signature on a message. And then all the generated signatures can be aggregated into one. So here, the signatures, instead of verify the signatures one by one generated by all the signers, here we only need to verify the aggregated signature. So here, it not only reduces storage space, but also reduces the task of the verifier. And the aggregate signature schemes, the BRS signature schemes, is already used in the Ethereum beacon chain. That in the beacon chain, that all the validators actually sign to do the attestations, and then it can aggregate like thousands of the signatures into one for the easy verification. Another way that helps doing the account management is threshold signature schemes. So a little different from the aggregate signature schemes and the multi-signature schemes, that each of the user will have a pair of public keys and secret keys to a digital signature scheme. What the threshold signature schemes do is actually it divided the secret key into pieces and distributed it among multiple devices. For example, here, the key is distributed into 3 parts, the secret key here, and we notice that any 2 of it can be recovered into the original key, and the original key can be used to do the signing. But actually, in the threshold signature schemes, the original key will never be recovered. They will use a multi-party computation protocol to generate the final signature. So in the threshold signature schemes can be used to build wallet. So at the first step, it will use some secret sharing schemes to distribute the signature signing key into pieces and store it in the multiple device or send to multiple parties. And then it will use multi-party computation to allow a threshold of people together to collaboratively sign a transaction. And this kind of wallet has been implemented by quite a lot of companies. So to do a comparison between the threshold signature wallet and the Bitcoin multi-sig wallets, the biggest advantage of the threshold signature wallets is that the signature that generated finally is a single signature, but in the multi-signature Bitcoin multi-signature wallet, but what actually generates is a set of signatures. So it reduces the signature size and also reduces the transaction cost. So another advanced signature schemes that utilized in the blockchain is linkable ring signature scheme. So it is another thing that focuses on the user's privacy. So for the ring signature schemes, it allows people to collect a bunch of public keys from other people and generate a signature. The signature will only demonstrate that, OK, this signature is generated from one of the corresponding secret keys of that bunch of public keys, but it will not reveal who exactly the signer is. So in this kind of cases, in the blockchain system, that if one person is allowed to, if one person collect other people's public key and generate a signature using the ring signature scheme, actually it can hide its identity. Of course, you need other tools to guarantee the authentication of the transactions. So the ring signature schemes is utilized in the blockchain systems like Monero to achieve an anonymous payment. And so here is some kind of advanced signature schemes. And then I'm going to talk about is the zero-knowledge proof. So zero-knowledge proof is a quite hot topic in the recent 2 years. And to explain it, I would say that a zero-knowledge proof is like a magician showing a magic to the audience. For example, like the magician tell the audience that, okay, I have a trick that for this currently look like not organized card, I have a trick that to immediately unshuffle it to let it become the organized version. So what the magician do is to demonstrate the, is to show the performance of the magic. So at last, what the audience see is, okay, the card is organized, but the audience will not know what exactly the trick the magician is used. So this is a kind of zero-knowledge proof that proves that the magician has a trick to do the unshuffle task, but the audience will only be convinced that, okay, the magician has this kind of power, has this kind of trick, but will not know what exactly the trick is. So if we use a more formal way to describe it, we would say that there is a prover and a verifier, that the prover tried to prove to verifier that, okay, for a public function f, I know some input x that could let the function output y. So the function here could be some kind of successful execution of a transaction or something like that. So after the running of the zero-knowledge proof, at the end, the verifier will output accept or reject to demonstrate whether it accepts or rejects the prover's statement. But the verifier will not know anything about the input x. So this is zero-knowledge proof. So for now, the most attractive types of zero-knowledge proof in the blockchain system is zk-SNARK. It is a zero-knowledge proof with additional properties. The first one is succinct. The second one is non-interactive. The non-interactive means that there will not be any interactions between the prover and the verifier during the proof process. Then the prover can just post a proof here and let the verifier to verify it later. And the succinct here means that the proof is very short and the verification task is very easy. So instead of letting the verifier to compute the fx, that could be much heavy computation compared with verify the proof. So the properties provided by zk-SNARK, zero-knowledge, succinct, non-interactive, and it is a proof, allows us to apply in the blockchain system. So the zero-knowledge focus on the user privacy part, the succinct focus on the efficiency and the scalability part. So here are some kind of zero-knowledge proofs application in blockchain. Let's start with the layer 2 scaling. So I know that some of you have already heard of ZK rollups. So in the ZK rollups, what they do is that on the layer 2 chain, there will be a lot of transactions, and there will be someone using a zero-knowledge proof to generate a proof to demonstrate that, okay, all of these transactions are valid ones with valid signatures, and it satisfies these state changes. And then the proof will be put on the layer 1 chain that, for example, like Ethereum. So this kind of setting allows the users to reduce the transaction costs that using the throughput in the L2 layer 2, but also take the advantages of layer 1. For example, its security, it's all those things, because the final proof, the validity proof of the transactions will be put on the layer 1 and using smart contract to verify it. Another application of zero-knowledge proof is cross-chain interoperability. So in some kind of cases, user may want to move assets from one chain to another chain. So in this kind of cases, that the zero-knowledge proof can be used to help people to generate a proof that, for example, here is a very simple like illustration here. So for example, on the sender chain, there will be some tokens locked in the smart contract, and then there will be a zero-knowledge proof generated to demonstrate that, okay, there are actually such a transaction to that smart contract that locked that much token inside it. And then the proof will be sent to the receiver chain, and there will be a smart contract there to verify the proof, and then the mint tokens will be sent to the receiver. So this is application of zero-knowledge proof in the cross-chain interoperability. And also, for the privacy part, the zero-knowledge proof cooperated with the ring signature schemes applied in the Monero to do the anonymous transactions and build the privacy-preserving cryptocurrencies. And also in Zcash and Alio, it used Zcash to hide the transaction details from the public. And also the Tornado Cash using zero-knowledge proof to do the coin mixing allows users to mix their cryptocurrencies with other users. So for now, there are actually quite a lot of ZK Snark. So ZK Snark is just like a concept, and you can use a lot of ways to build a ZK Snark systems. And here is just some of them, and they have different setups. For now, the zero-knowledge proof, the ZK Snark that with shortest proof size is this one. So because we know that in the blockchain world, the proof size is very important. The small proof size means small transaction cost. And also, I will talk about our work in the zero-knowledge proof field that one big challenge of applying zero-knowledge proofs, especially ZK Snark in the real world, is about the prover's efficiency. That the proof's task on generating such a proof is very heavy. So what we do and what we've researched is about the ways to reduce the prover's task on generate the proof. So our work has been recognized by the zero-knowledge cryptography competition and received more than 800,000 USD cash award. So for the first task, for the first work, we are looking at the proof generation for a general ZK Snark proof. So what we do is two parts. The first one is using the hardware acceleration to accelerate the proof generation, and the second part is to use the distributed power to distribute the proof generation. So the hardware acceleration allows us to use GPUs to accelerate some kind of mathematical operations inside the ZK Snark to make it faster. And also the distributed proof generation is actually targeting on the memory thing, that if we use one single machine to generate a zero-knowledge proof, the memory usage could be like very, very large. So, but if we distribute it into multiple machines, then we only need to use several like machines with small memories instead of using a very powerful machine. So here, for example, like we have such a zero-knowledge proof system that requires that many mathematical operations. Here, the FFT means some kind of heavy mathematical operations. So what we do is that first we like redesign the algorithms and to distribute it into multiple machines. Here it is a very simple illustration. And also in each of the machines, it will equipped with GPUs to accelerate this kind of mathematical operation. So here, for example, like in our experiment for circuit, so here the circuit is like this, how complex your statement you're gonna prove. So the proof for a circuit with 2 to the 28 gates, so it is a very complicated statement that you're gonna prove. Originally, the prover would typically need at least 1 TB of memory, but after the distribution and some other redesign of the algorithms, we can use several smaller machines, and the total memory becomes 450 GB. And another task is about to accelerate the proof generation for a specific task is the signature verification. So the signature verification, especially for the ECDSA signature is utilized in Bitcoin or Ethereum or other blockchain systems as the users used to generate users account. So here we can see that it is the most widely used digital signature schemes as of today. So verifying ECDSA signatures using the ZKP allows us to connect on-chain data along with the off-chain like other apps. So in this work, what we do is that we reduce the constraint numbers required to verifying messages in the ECDSA ECDSA signature. So it is specifically targeting on improve the efficiency for ECDSA signature verification. And so what we've achieved is that we reduce the originally, it requires 50 million constraints. So the constraints is also like the circuit size. It is related with the statement complexity. But we reduce it to 6.2 million constraints. So which means that work on the prover side is going to be a minimum of 8-fold reduction. So here's my talk about the role of cryptography in the blockchain. Thank you.
Thank you very much, Dr. Liu, for illustrating the central role of cryptography that plays in blockchain security and sharing your own experience as well. And our final speaker for today is Dr. Ning Yu He, Research Assistant Professor in the Department of Computing at the Hong Kong Polytechnic University. Dr. He will share on the topic, the hidden cracks in Web3, how implementation inconsistencies are breaking Ethereum's promise. Please welcome Dr. He.
Okay, thanks for your introduction. And hello, everyone. And my name is Ning Yu, and I'm a research assistant professor at PolyU. So the disclaimer first, this is a set of work, or specifically two work, that is done with me and a BOA PhD student, that is Jiema. So as you can see in the title, so our topic is about how implementation inconsistencies are breaking Ethereum's promise. So first of all, as a participant, you must know the importance of Ethereum, right? So I will give you some simple numbers. So first of all, we know that smart contract is a killer application of Ethereum, right? So based on smart contract, we have lots of DeFi protocols and dApps and some other things. And currently, as of June 2025, we have more than 70 million smart contracts that are deployed on Ethereum, and with 32,000 of them are deployed every day, and total value locked in DeFi hit 65 billion. So, as a user of Ethereum, we must use Ethereum, right? So this is a simple graph that how we use Ethereum. So this is us, and this is a node. So actually, we interact with Ethereum with the APIs provided by Node, that is RPC. So we send a request, and the node will give us some response. So the request includes some, like, you can query blockchain state, like retrieving account balance, smart contract state, and transaction history, and block information. And of course, you can use a node to send some transactions, like you can transfer in your own Ether, like some tokens, and calling other smart contract functions or deploying some new contracts. But we know that Ethereum is a worldwide ecosystem. So because of some physical limitations, the data transmission takes a certain amount of time. So node will receive different transaction data at some point. So this will result in some inconsistency between nodes. So we know this issue. So Ethereum proposes some solutions. So the obvious one is the consensus algorithm. The consensus algorithm is proposed for maintaining the consistency of states among all these nodes. So if we break down the node here, we can say, okay, after the merge, that is the POS of Ethereum, we can we have two clients in one node. That is consensus client and execution client. So in the consensus client, it is responsible for handling some consensus problems like consensus logic, fork choice, block gossip, and beacon API. And in the execution client, that is something we are familiar with. That is transaction handling, transaction gossip, EVM, state management, and JSON RPC. So in this figure, so where can the inconsistency emerge? So I will give you two attack vectors we are focusing on. So the first one is EVM. So what about you give the node with an identical OP code or an identical smart contract, but different nodes will have different response. So the second attack vector is that, okay, what if we give node an identical request, but different nodes will have different response. So this is how inconsistency emerge. So I will give you our first work. This has been published on ISTA. This is a software engineering conference. So in the first one, we talk about the EVM. That is, we find that an identical smart contract will lead to different behaviors in these nodes, especially in the EVM. So I will give you our motivation. So we focus on this work because of two reasons. So the first one is that, okay, currently we have a lot of existing tools like fuzzers, static analyzers, symbolic executors, and all these things focus on smart contract security. But the security of the underlying EVM is less researched. So you can see this figure, and currently we focus on the smart contract, and lots of you talking about the DeFi protocol security or DApp security, but what about the execution environment, that is the EVM? What if there were some problems in the EVM? So the second reason is about, okay, the EVM deficiencies could lead to some inconsistency issue, and there is an obvious one, that is a CVE, which has triggered a chain fork on Ethereum mainnet in April 2021. So we underline that detecting EVM implementation bugs is essential for Ethereum security. And, okay, let's talk about EVM more in detail. So when we talk about EVM, actually EVM is a kind like state machine to handle the world state of Ethereum. So if we talk about the state, we have two types of state in Ethereum. The first one is machine state. So the machine state is volatile or temporary, or it will disappear after the transaction. It includes some program counters, stack, and memory, and gas. And we have another type of state in Ethereum, that is a world state. So the world state is persistent, or it is forever. It will exist as long as the Ethereum exists. So it has some long-term data, like account balance, some storage, or the deployed contract. These are all included in the world state. And EVM, of course, takes the smart contracts bytecode as input. So we do a preliminary study, and we found, okay, there are lots of implementations of EVM right now. We have some standalone EVMs like PyEVM, EVM1, Ethereum JS, or REVM. And also we have some execution clients like the GAS we use every day, and Nethermind, the Basu, and Aragon. And we have some other EVM compatible chains like BNB, Polygon, Avalanche. So all these EVMs has an identical functionality. That is, you have to give an identical response once you are given an identical smart contract, right? So this is our motivation. We use differential testing. What is differential testing? That is, you give an identical contract bytecode, you send it to different EVM, they should respond, they will output the state, right? The world state and the state defined here. And you can observe the difference of all this machine state and world state between these EVMs. If there are some fields that are different among with each other, that is something bad, right? So this is our design method. First of all, we use Ethereum specification for OP code, and we use large language model to construct some smart contract, and we do some mutation to enrich the semantics of the smart contract, like we do some control flow mutation and argument mutation. And then we send the generated smart contract to our differential testing phase. In the differential testing phase, we included all these EVM implementations, and we send this smart contract to these EVM implementations, and we try to figure out, okay, if there was something different, among each other in terms of return data, gas usage, or storage. And we will do the manual investigation to find the root cause of these bugs. So here is our included EVM clients. As you can see, we have included 9 EVM and including more than 95% of execution clients and all official standalone EVMs and 2 custom EVMs. And we use some baselines as, we use some fathers as baseline, and we use GPT-4o. And this is our result. As you can see, our tool, OP-Differ, has detected 26 bugs across all these 9 EVMs implementations, and including some mainnet clients, some standalone clients, and the third-party EVMs. And more than 80% of them has been fixed or confirmed, and 3 bugs has even received the CNVD vulnerability IDs. And as you can see, we even figure out some OP code bugs in GAS and Bosu. And here are 2 case studies. So the first one is the buggy implementation of self-destruct in PyEVM. So in PyEVM, we know that mnemonic is a mandatory field of each OP code, but the PyEVM forgot to include the mnemonic field in the self-destruct. So when you send a smart contract to an EVM, that is a PyEVM, it will crash. And the second is that pref rundown, this is a new OP code, but in GAS, they forgot to add these fields in their implementation, that is GAS. So it will also go crash when it handling some smart contract containing the pref rundown. And the second one, this one is under submission. So this one, we talk about the RPC, that is a request and response. So why we focus on this? So this is a real-world bug, and we take this as our motivation example. So you must familiar with these 2 figures. These are screenshots for EtherScan. And as you can see, for an identical transaction, this is 0x897. The state difference or the transfer value is different. The first one is 10 cents, and the second one is 1 cent. So why this happen? This is because EtherScan use the API provided by Aragon as a data source. So even an identical request to Aragon, the Aragon will respond differently in this transaction. So this is our motivation example. So in this work, we do a preliminary study first, and we have included all 5 mainstream execution clients and all 6 consensus clients. So this is the execution client and the consensus client we included in our work. And the execution layer clients and actually are the primary entry point for receiving user requests, like handling user transaction submissions, account queries, and smart contract calls. And the consensus layer clients, we may not familiar with this because they do not handle requests from user directly, but through the engine API, that like a bridge between the execution client and the consensus client. But in this work, we expose the engine API to the users to do the test. So this is our method. And first of all, okay, we still based on the specification that is provided by Ethereum. And this one is about the this one is RPC specification. And we use this specification, we generate lots of RPC requests, and we do some mutation. And in this mutation, we include some syntactically invalid and also some invalid input. And we do some semantic mutators. So we have syntactically and semantically rich RPC requests. And we send this request to different nodes. So you must remember differential testing is about, OK, a node must respond identically for an identical request, right? So we have 30 combinations because we have 5 execution clients and 6 consensus clients. That is 30 combinations. So we construct these 30 combinations as nodes and deploy it in our local testnet, and we send the constructed RPC request to these 30 nodes. And we try to figure out if they behave different. And we try to figure out and we generate a bug report. So these are the results we have found. Actually, in total, we have figured out more than 50, that is 58 bugs. And 53 of them have been confirmed. And 3 bugs, we also, interestingly, we found 3 bugs in the specification. That is the bottom right corner. So we try to figure out the impact of these bugs or vulnerabilities. So we follow the CWE, that is Common Weakness Enumeration. This is a category system. And we try to, we manually interview all these bugs and we split all of them into this CWE category system. And we figure out, okay, there are bugs everywhere. And all execution client and consensus client have API bugs. And same bug, for a same bug, they have different attitudes. For the same API bug, and different team will have various opinions. And we also find some specification bugs defined or provided by Ethereum official. And this is a case study. So as you can see here, this is a specification bug. That is, the min items and the max items for this RPC response should be 33, but in the specification, they are 32. And in the specification, they should include this field, that is blob gas used, but they missed it. So this is a specification bug, and the reported bug has received some positive attitude, and this bug has even escalated to the Ethereum project management meeting for discussion. And finally, we have some key takeaways. So the first is we have some critical consistency issues exist across the Ethereum ecosystem. And in this two work, we uncovered serious inconsistency problems between different EVM implementations and node APIs, which undermines Ethereum's promise as a reliable decentralized platform. And the second one is, okay, there are widespread implementation bugs discovered, and we have identified 26 bugs across 9 EVM implementation and 58 bugs in Ethereum node APIs, and demonstrating the implementation inconsistency are pervasive or widely spread. And the third one is that all these mainstream clients are affected. And the bug exists in all execution layer and the consensus layer clients, and indicating this is a system risk, and rather than some isolated problems in specific implementation. And the last one is the specification gaps compound the problem, because we found some bugs in the specification, of course, and we can migrate this method to other platforms. This is not a problem in Ethereum. We can migrate it to Bitcoin, to Solana, to some other platforms. And I think there are also some other attack vectors in the node, except for the EVM and the RPC interface. So I think this is a set of work, and we will do much more in this area. And thank you.
Thank you very much, Dr. He, for the thought-provoking perspective on Ethereum and scrutinizing the challenges of Web3. And ladies and gentlemen, this concludes our PolyU Spotlight, building a reliable and secure Web3 session. On behalf of the Hong Kong Polytechnic University and the Research Center for Blockchain Technology, once again, thank you for all 4 speakers for sharing their expertise, and thank you everybody for joining us today at WOW Summit Hong Kong 2025. Before we officially close, we'd like to invite all speakers on stage for a group photo. Speakers, please.
Oh, they're doing one last photo off the PolyU.
For guests on the floor, we've prepared souvenirs on the right-hand side of the stage, so please seize the chance and grab your souvenir.